The Delta-Wye connection of distribution transformers presents several advantages when contrasted with the Wye-Wye configuration. Firstly, it facilitates a reduction in neutral current. The Delta-Wye connection fundamentally eliminates the need for a neutral wire, which in Wye-Wye systems typically conducts unbalanced current stemming from the loads connected to the system. This reduction in neutral current is particularly advantageous in systems that experience significant load imbalances. By minimizing the current flowing through the neutral conductor, the Delta-Wye connection helps to reduce voltage fluctuations across the system, thus enhancing overall system stability. Secondly, voltage regulation is improved. The Delta-Wye connection provides superior voltage regulation capabilities compared to the Wye-Wye connection. This enhancement arises from the inherent properties of the delta winding, which effectively acts as a voltage stabilizer. The delta winding works to maintain a more consistent voltage level on the secondary side of the transformer, regardless of variations in load or input voltage. Thirdly, fault current limitation is enhanced. The delta connection on the primary side of the transformer plays a crucial role in limiting the magnitude of fault currents that can occur during a short circuit event. By limiting the fault current, the transformer is less likely to sustain damage or experience failure as a consequence of the fault condition. This protection is vital for ensuring the longevity and reliability of the transformer and the overall power distribution system. Fourthly, the connection reduces harmonic distortion. The Delta-Wye connection is effective in mitigating harmonic distortion within the power system. The delta winding functions as a low-pass filter which attenuates higher-order harmonics present in the system. This filtering action improves the overall power quality by reducing the adverse effects of harmonics on sensitive equipment connected to the grid. Harmonics can cause overheating, interference, and other performance issues in electrical devices, so minimizing their presence is crucial for maintaining a stable and efficient power system. Fifthly, ground fault protection is also improved. The Delta-Wye connection enhances ground fault protection capabilities. The high impedance of the delta winding limits the current that flows during a ground fault condition. This limitation makes it easy to detect and isolate the fault without causing widespread outages or damage to equipment. By quickly identifying and addressing ground faults, the Delta-Wye connection ensures a safer and more reliable power distribution system. Sixthly, the transformer provides for an increased power transfer capacity. In certain scenarios, the Delta-Wye connection can increase the power transfer capacity of the transformer. This is attributed to the fact that the delta winding is capable of handling higher voltages and currents compared to the Wye winding. The increased capacity allows the transformer to deliver more power to a load without exceeding its design limitations. In summary, the Delta-Wye connection is generally preferred for distribution transformers, particularly in systems that are subject to unbalanced loads or where voltage regulation, fault current limitation, and improved power quality are critical considerations. The specific advantages of the Delta-Wye connection, such as reduced neutral current, enhanced voltage regulation, and effective fault current limitation, make it a robust and reliable choice for modern power distribution networks. When selecting a transformer connection, it is essential to consider the specific requirements of the application and weigh the benefits and drawbacks of each configuration. The Delta-Wye connection offers a compelling solution for many distribution systems, providing enhanced performance, improved reliability, and greater overall efficiency. Further elaborating on the aspects related to Delta-Wye transformer connections, it is important to consider the implications of the connection type on the system's grounding scheme. The Delta-Wye configuration inherently isolates the neutral point and the delta side, which can be beneficial in certain applications but requires careful consideration regarding grounding on the Wye side. One common approach is to ground the neutral point of the Wye winding, which provides a reference point for system voltages and helps to stabilize the system under fault conditions. Different grounding methods, such as solid grounding, resistance grounding, and reactance grounding, can be employed depending on the specific requirements of the system and the desired level of fault current limitation. Solid grounding provides a low impedance path for fault currents, which can result in high fault currents but also allows for rapid detection and clearing of faults. Resistance grounding introduces a resistance in the ground path, which limits the magnitude of fault currents and reduces the stress on equipment during a fault. Reactance grounding uses an inductor in the ground path, which can provide similar benefits to resistance grounding but may also introduce resonance issues under certain conditions. The selection of the appropriate grounding method depends on factors such as the system voltage, the available fault current, and the sensitivity of equipment to voltage disturbances. Another aspect to consider is the impact of the Delta-Wye connection on transformer impedance and short circuit capacity. The impedance of the transformer is a critical parameter that affects the magnitude of fault currents and the voltage drop under load conditions. The Delta-Wye connection can influence the transformer impedance, particularly the zero-sequence impedance, which is relevant for ground fault calculations. The short-circuit capacity of the transformer is a measure of its ability to withstand fault currents without sustaining damage. Transformers with higher short-circuit capacity are generally more robust and can better withstand the stresses associated with fault conditions. The Delta-Wye connection can also affect the transformer's ability to handle imbalanced loads. Imbalanced loads can cause voltage imbalances and increased losses in the transformer. The delta winding helps to mitigate the effects of unbalanced loads by providing a path for circulating currents that tend to equalize the voltages on the secondary side. However, it is still important to carefully consider the load balance when designing and operating a Delta-Wye transformer system. In addition to the technical aspects, it is also important to consider the economic factors associated with Delta-Wye transformers. Delta-Wye transformers may be more expensive than Wye-Wye transformers due to the more complex winding configuration and the additional insulation requirements. However, the benefits of the Delta-Wye connection, such as improved voltage regulation and reduced harmonic distortion, can often justify the higher cost. Furthermore, the longer lifespan and reduced maintenance requirements of Delta-Wye transformers can result in lower overall lifecycle costs. When selecting a Delta-Wye transformer, it is important to consider the specific application requirements and to consult with a qualified electrical engineer to ensure that the transformer is properly sized and configured for the intended use. The selection process should take into account factors such as the load characteristics, the system voltage, the fault current levels, and the grounding requirements. By carefully considering these factors, it is possible to select a Delta-Wye transformer that provides optimal performance, reliability, and efficiency for the specific application. Moreover, the use of advanced simulation and modeling tools can help to optimize the design and operation of Delta-Wye transformer systems. These tools can be used to analyze the performance of the transformer under various operating conditions to identify potential problems and to evaluate the effectiveness of different mitigation strategies. Simulation and modeling can also be used to optimize the transformer's parameters, such as the turns ratio, the impedance, and the grounding configuration. In addition to the technical and economic aspects, it is also important to consider the safety aspects of Delta-Wye transformers. Delta-Wye transformers, like all electrical equipment, can pose safety hazards if not properly installed, operated, and maintained. It is important to follow all applicable safety codes and standards when working with Delta-Wye transformers. This includes using appropriate personal protective equipment, following lockout/tagout procedures, and ensuring that the transformer is properly grounded. Regular maintenance and inspection of Delta-Wye transformers are also essential for ensuring their safe and reliable operation. Maintenance activities should include checking the oil level, inspecting the bushings and connections, and testing the insulation resistance. Any problems that are identified during maintenance should be promptly addressed to prevent the equipment failure and potential safety hazards. Furthermore, the use of smart grid technologies can enhance the performance and reliability of Delta-Wye transformer systems. Smart grid technologies such as advanced metering infrastructure, distribution automation, and remote monitoring can provide real-time visibility into the operation of the transformer and the surrounding power system. This information can be used to optimize the transformer's performance, to detect and diagnose problems, and to improve the overall reliability of the power grid. In conclusion, the Delta-Wye connection offers numerous advantages over the Wye-Wye connection for distribution transformers. These advantages include reduced neutral current, improved voltage regulation, enhanced fault current limitation, reduced harmonic distortion, and improved ground fault protection. The Delta-Wye connection is particularly well suited for systems with imbalanced loads or where voltage regulation, fault current limitation, and improved power quality are important considerations. When selecting a Delta-Wye transformer, it is important to carefully consider the specific application requirement and to consult with a qualified electrical engineer to ensure that the transformer is properly sized, configured, and operated. By taking these factors into account, it is possible to select a Delta-Wye transformer that provides optimal performance, reliability, and efficiency for the specific application.